Hello and welcome to episode 4 of the Civboot podcast, designing and fabricating a Civboot integrated circuit. Before I get into this though, I just want to talk a little bit about why there was a little bit of a gap between episodes. Mainly it's because I kind of went on a tangent of learning FPGAs and learning about FPGAs and learning about the different tools and starting a tutorial on FPGAs and Verilog. And I'm going to talk about that in this episode because it's actually very essential for designing an integrated circuit, at least doing it in an open source fashion that can be replicated by others. The other thing I want to talk about is I do have a baby. She's 5 months old, and she takes a lot of my time. And I have 2 other children as well, both very young. So I just want to reiterate, this is a lifelong goal, something I want to accomplish in my lifetime. There's no rush for me to accomplish this. So the episodes will come out when they come out, and the work I do will happen when it's done. I have a full-time job and a full-time family. So I just wanted to give that as a heads up for any listeners, because I do have a few now, 8 subscribers. Ooh, exciting. Thank you so much for listening. I really appreciate that people are interested and that they enjoy this podcast. But to get on with it, this episode is about chip manufacturing and design, and it's after the semiconductor manufacturing, episode 2. This is very high-level stuff. I'm not going to be going into depth here. Going into depth for this kind of learning requires college graduate level work. This is one of the harder things a Civboot would be trying to do. And also, I think it's important to note, my overview is not that great probably, but you can see the show notes and the accompanying blog post for some links to better overviews. I'm going to be mostly talking about how the chip manufacturing would relate to a Civboot, rather than try to go over the material in depth. Hopefully in a future episode, maybe when I'm a graduate level or get a PhD in learning wafer manufacturing, which I kind of have an intent to do. I've kind of always wanted an excuse to do it. This is a good chance. Maybe then I would be able to put out some of that kind of material. But let's talk about the basics. How do you make a computer chip? Because this is obviously essential for a Civboot to be able to work. So you start with a very thin, pure silicon wafer, which again we talked about in episode 2. The first thing you typically do is you oxidize it. So you make silicon dioxide on the top, and that seems kind of odd because you started with silicon dioxide that was sand, but there's a reason for that. The oxide protects the underlayer. Most ICs you have today have a layer of oxide over them for protection from corrosion, essentially. So you first oxidize it. It's also used extensively in the wafer processing, we'll see. After oxidizing, you apply what's called a photoresist evenly over the top. They just spin the wafer, basically. They put a little bit of photoresist. It's a liquid, and they spin it. It applies a very thin layer of what's called photoresist, and then they use a mask and light. And for positive photoresist, when you then the areas that were exposed to light then dissolve with a solvent. Like I'm not sure what they use, but I think like alcohol would be an example of a solvent that I think you can use. And so that dissolves away some of the photoresist, and so you have some areas that are protected and some areas that are not protected. And then you can apply a range of processes. This is the basics of how integrated circuits are made. So you can dope the material. There's 2 ways to do this, but the most basic is you have like some boron on a rod, you heat up the boron, and it shoots atoms of boron down in very small quantities and gets injected into the silicon lattice. Which makes the silicon slightly doped, have a very small concentration of boron inside of its pure silicon lattice, and this makes it slightly, depending if it's boron or another material makes it slightly p or n typed, positive or negative, which gives it holes or electrons that are free to move around and carry charge. And that the physics of that are somewhat complicated. I'm not going to get into it in this episode, but that is the basics of how a wafer is made. Oh, in addition to doping the material, you can also do things like add metal, so you can have metal contacts and wires to go between transistors. Then, once you've manufactured the integrated circuit through that very high level process, you cut or break them off. You can do what's called a score and cleave, which is actually quite effective because the silicon lattice is a perfect crystal. If you can make a cut or break, the crystal is guaranteed to break perfectly straight. I've actually done that. It's kind of fun, honestly. And then you can wire bond the integrated circuit to the integrated circuit, which is the thing you actually solder. So when you solder something, you're not soldering the pure silicon material. You're soldering a plastic housing that has metal contacts, and those metal contacts have been wire bonded typically to the chip. So that's it. The processes to achieve many of these steps and the complexity in them is extreme and requires very high precision, even for the density of transistors that a Civboot would need. Well, this process is likely easier than growing a pure semiconductor. That's pretty hard. Growing a pure semiconductor is very difficult, reaching the purity levels you need. It's very far from easy. It is, however, I should point out, easy enough that there's a teenager, a very brilliant teenager, I'm sure his name is Sam, and he managed to build a simple integrated circuit, and from the wafer all the way to building an integrated circuit, wire bonded circuit, in his garage. Now, he did use highly expensive, or typically very expensive, legacy tooling, which he acquired through various means from eBay and I guess some colleagues, or some friends of his, some friends. And you should definitely check out his link. He has a full video tutorial on how to make integrated circuits. Very worth checking out if you're more interested in the details of how to make a transistor, essentially. But that's about all I'm going to cover here in this podcast. You should also check out an excellent, I think it's about 11-minute video. It's not very long, which is by a semiconductor manufacturing company. And they have an excellent educational overview of just how a transistor is made with great pictures and everything. I highly recommend that as well. Maybe do that and then maybe check out Sam's work. But the next thing, or maybe the first thing, we're getting the cart in front of the horse here a little bit. Before you build your chip, you need to know what you're building. So you need to know what transistors you want and how you want to wire them together. And you need to know that generally works. You don't want to go and fabricate a chip typically unless you have a good idea that it works. So how do you do that? Well, obviously the first way you can do it, you could simulate it in software. And that's very useful. There's software packages that do that. But more interestingly, and this is kind of mind-blowing, especially if you've never heard about them, are field programmable gate arrays, FPGAs. What is an FPGA? An FPGA is a computer chip. It kind of is like a logic chip merged with a memory. So you can think of it as it's got a bunch of transistors and it's got a bunch of wires, but whether the wires connect to the transistors and where they connect to the transistors is determined by a parallel memory unit. So you write some memory and then you get transistors connected together in many configurations. Now, why would you want to do this? Turns out with just that, and I'm glossing over it a little bit, there's different logic units, there's different transistors that you can connect, but basically that's how it works. with just that design, you can write the logic for what you want your CPU to do. You want an adder, you want a subtractor, you want this register here, you want that register there, you want this kind of instruction to take a clock cycle and do this, this, and this, and this, and then write the result to some register or some memory or whatever, right? That's what a CPU does. You can write that logic in a programming language called Verilog, very different from many other programming languages, because you have to deal explicitly with the clock, among other things. And you can have, there's many differences. You can check out how Verilog works, but use a programming language called Verilog, and you can program onto the FPGA your CPU and actually run physically your CPU on the FPGA at a fairly high clock rate. So it's not virtual. It is your CPU running on that thing. And so you can prototype your CPU. You can put just the FPGA on a board with all the peripherals like the input outputs and power and everything. And you can create your custom chip, essentially, there to prototype it. Now, this is very useful for Civboot, very useful for development of new computer chips, which Civboot will need to do that. I fully intend to utilize FPGAs, especially at the beginning of Civboot. Also, recent development, pretty recent, if you don't keep track of FPGAs, I think it's in the last 5 years or so, certainly. There are now open source tools for programming FPGAs. This is extremely exciting for me. There's a project called Project Ice Storm for programming a few specific kinds of FPGAs, and there's other work being done to try and break into being able to program Xilinx, which are like the Intel of FPGAs. And I also link to an excellent FPGA tutorial that is in English and Spanish, which I am going through right now. Although I will be switching to do something else because, like I said, time is limited, and I think I want to focus on the fourth implementation first. But that tutorial is excellent. I have an FPGA right here. It's got a little breakout board. This one has a little bug on it. I'd recommend. This one's made by Alcatraz. I recommend waiting a little bit and having them fix it for the I/O top there. It's got like some buttons. The buttons don't actually work, but the switches and LEDs work. Anyway, I intend to use a fourth, for the FPGA stuff, I intend to use a fourth CPU that's been made as my basis called the J1. I want to modify it a little, make it a little more general purpose, specifically be able to access more memory regions. I'm trying to think of what the best way to do that would be. I have some ideas, but nothing concrete yet. And it might also be worth mentioning that there are such a thing as what's called Homebrew Computers. The number of things you come across when you're researching for a Civboot is pretty amazing. It's called Homebrew Computers. It's people building computers at home, some of them out of very limited parts. One of my favorite it's called the Mega Processor, and it's made entirely out of discrete transistors, single transistors. It takes up an entire large room, but you can see all of the transistors working. It's got LEDs as well to show how it's computing things, and it's very interesting. It's a worthwhile video to watch. So that's a little bit of things that you could look at if you're interested in this kind of work. Also, it's worth mentioning that open silicon is starting to become a thing, starting to become more common. That some of these wafer fabrication processes may start to be more public domain in the future. So there's a company called lowrisk.org, and other toolkits are available for developing these chips open source. I should also mention, and I've mentioned this before, developing a Civboot CPU that is built in a Civboot is like a 30-year goal. The first Civboot tooling will definitely be on an FPGA. Obviously, that's not built into Civboot. Eventually, maybe Civboot may order their own integrated circuits that they've designed, that Civboot has designed, through standard wafer processing facilities. So not growing our own silicon or anything. That is how it's going to be iterative. We're not going to just start with sand and make a CPU. There will be a mix of proprietary built open source CPUs and eventually Civboot completely open CPUs for a long time, even when we can make our own CPUs, because the first CPUs we make, if we ever make them, like I said, in 30 years or more, it's going to be hard to make them, and we're probably not going to be able to make as many as we want, and they probably won't have the reliability we want. So this is iterative, and that's okay. Reducing the complexity of knowledge, getting all of the layers right will take time. It will take effort. It'll take a lot of attempts, a lot of dead ends, and that's okay. So with that, thank you so much for listening, and I hope you have a happy holidays, and good day.